Calculating molar enthalpy of solutions. As explained in video number 22, when some solutes dissolve in water, they are accompanied by enthalpy changes. For example, when sodium hydroxide is dissolved in water, there is a rise in the temperature of the solution that is formed, as indicated by the equation below. Here we are seeing how solid sodium hydroxide crystals are getting dissolved in water to produce a solution of sodium hydroxide with the liberation of energy. And this energy change is called enthalpy of solution. The molar enthalpy of solution for a particular solute can be measured using calorimetry. To do this, the following steps are carried out. Step number 1. A known volume of water is placed in a styrofoam cup. Number 2. The initial temperature of the water is measured. Number 3. A known mass of a solute is dissolved in the water by stirring. And finally, the final temperature of the solution is then taken. The following problem is used to explain how the molar enthalpy of a solution for a particular solute is calculated. In this sample problem, 4 grams of sodium hydroxide is dissolved in 200 milliliters of water, and its temperature is changed from 20 degrees Celsius to 26 degrees Celsius. If this change took place in a styrofoam cup, you're asked to calculate the molar enthalpy of solution for sodium hydroxide. So the solution is as follows. In this case, as in every other case when solutes are dissolved in water, the heat that is produced is absorbed directly by the sodium hydroxide solution formed. And since the solution is dilute, we shall assume that it has the same density as water to calculate its mass and subsequently its enthalpy change. And of course, we also assume that the solution will have the same specific heat capacity as water. So here's the solution. First of all, we identify the given quantities. The mass of the solution is 200 grams. A point to note is this, that the mass of the dissolved solute is not added to the mass of the solution. In this example, the mass of the solution is assumed to be the same as the mass of water. The 4 grams of NaOH is not included. So to emphasize that, we have 200 milliliters of water. Obviously, if someone has 200 milliliters of water, and you add 4 grams of a solute to that, then the total mass of the solution should be 204 grams. But this is the assumption that is made when you're doing calorimetry to find the molar enthalpy of solution. The mass of the solid is not added to the mass of the water that was initially used. So that's the mass of the solution. This is a specific heat capacity for water that we'll be using in this case. And the change in temperature is 6 degrees Celsius. Its initial temperature was 20 degrees and its final temperature was 26 degrees. And that's why you have delta T is equal to 6 degrees. And this is the mass of the sodium hydroxide that was used. So this is the deal. If you have a styrofoam cup and it has the solution here, then the solution is what absorbs the energy that is produced. So the 200 grams of solution will absorb the heat that is produced as a result of the solution process. And to find the amount of energy produced, we use this equation here, Q is equal to mc times delta T, and of course you know Q will be equal to your delta H. So the heat that is produced is equal to 200 times that, times 6, and that is what it is. This enthalpy change is for only when 4 grams of sodium hydroxide is dissolved in water. Now we have to find how much energy is produced when 1 mole of sodium hydroxide is dissolved in water. But first of all, we have to calculate the number of moles of sodium hydroxide that was used in this process. And to find that, we'll take its mass and divide it by its molar mass, and it works out to be that number of moles. Recall that the molar enthalpy change for any reaction is given by this equation here that we talked about in a previous tutorial. The delta H of solution in this case will be equal to delta H over the number of moles that was used. So to find the molar enthalpy change for a solution for sodium hydroxide, we'll take Q, which is delta H, and divide that by the number of moles, which is 0.01 mole in this case, and it works out that the molar enthalpy change of solution for sodium hydroxide is equal to that. So one more time, we have 200 milliliters of water and 4 grams of sodium hydroxide is dissolved inside. The rule is that do not add the mass of solute that is dissolved in the water when you do your calculation. The temperature was changed from 20 degrees Celsius to 26 degrees Celsius. So we're saying that the heat that is produced is absorbed by the aqueous solution that is formed. So if you have 200 milliliters of solution, then whatever heat is produced is absorbed by it. So finding the heat produced will represent the enthalpy change for this dissolving of 4 grams of sodium hydroxide in this 200 milliliters here of solution. So using this formula, we got the heat produced to be this, and we said that was equal to delta H. The next thing we did was to find the number of moles of sodium hydroxide. Turns out to be that. And then using this formula here that is used for calculating the molar enthalpy change for anything, delta H divided by N, we ended up with that value there. Now we shall show how we calculate the enthalpy of neutralization. This thermochemical equation here represents a reaction between sodium hydroxide and hydrochloric acid. Here you see they reacting in a ratio of 1 mole to 1 mole to give a solution of sodium chloride with the evolution of energy. The point of emphasis is this. During a neutralization reaction, effectively what is happening is hydrogen ions neutralizing OH ions. If we did the ionic equation for this reaction here, you can see we're taking out all the spectator ions. We are left with a net ionic equation, and basically this is what is happening during a neutralization reaction. Hydrogen ions neutralizing OH ions, vice versa. And that is the change that is responsible for producing the enthalpy change. Again, calorimetry will be used to calculate the molar enthalpy change for this neutralization reaction. But one thing to note is this, is that the enthalpy change produced is caused by both the hydrochloric acid and the sodium hydroxide reacting simultaneously. So we're saying that the molar enthalpy change produced can be attributed to either the base or the acid separately. It's like in a marriage between a man and a woman, a child is born. Either parents can make claim to that child. In a similar way, when an enthalpy change is produced during a neutralization reaction, either the acid can make claim to the enthalpy change separately, or the base can do the same. To find the enthalpy of neutralization, the initial temperature of the base and acid must be the same to start with. Number 2, equimolar quantities of hydrogen ions and hydroxyl ions must be used. If not, the limiting reagent must be found and be used to calculate its molar enthalpy of neutralization. Let us suppose that you added more acid than base. It doesn't matter how much excess acid is added, it will not be neutralized unless we increase the amount of base. So if the acid is in excess, the OH ions will be the limiting reagent, and then we have to use the limiting reagent to calculate the molar enthalpy of neutralization. Next, the two reagents are then mixed and stirred in a styrofoam cup. So we know their initial temperatures, we know their initial volumes, and then the final temperature of the mixture is recorded. The final mass of the mixture, of course, will be equal to the volume of the acid plus the volume of the base. The following sample problem is used to show how the molar enthalpy of neutralization for the reaction between sodium hydroxide and hydrochloric acid is calculated. So here we are having 50 milliliters of 1.0 mole per liter HCl at 20 degrees Celsius, and we're taking the same volume and of the same concentration of sodium hydroxide at 20 degrees Celsius. So two things are common here. One, the initial temperatures for both are the same, and because these are monoprotic base and monoprotic acid, you have equal concentration and volume that will give the same number of moles of OH ions and H ions. Of course, these are poured into a styrofoam cup and the mixture is stirred, and the final temperature of 23.2 degrees is attained. And now you're asked to calculate the molar enthalpy of neutralization for either sodium hydroxide or hydrochloric acid. So we have some figures here to make matters easy for you. This is the volume of HCl and concentration and initial temperature, and is the same here for sodium hydroxide. Well, look what happens. When you mix these guys, a final volume of 100 milliliters of sodium chloride solution is produced with a final temperature of 23.2 degrees. So what we can say here is that this volume of mixture here, which is equal to 100 milliliters of sodium chloride, is what will absorb the heat that is produced. We know a number of things here. We know the final mass will be 100 grams. We know its specific heat capacity is assumed to be the same as that of water, and we can subtract 20 from this and get delta T. So let's see how the calculation is done. These are the given quantities. This is the mass of the solution produced. So we assume every milliliter weighs 1 gram. Since we're assuming that it is the same as water, the specific heat capacity is assumed to be the same as that of water, and delta T is 3.2 degrees Celsius. Again, we'll use this equation here, Q is equal to MC delta T, which is the same as delta H. This will be the mass because it's 100. Multiplying those quantities, we end up with that number of joules for delta H. Up to this point, the enthalpy change is not for 1 mole of either the base or acid. The number of moles of the acid is found using N is equal to C times V, and that's the number of moles produced. Same thing for sodium hydroxide. In both cases, the number of moles is the same. Alright? So again, we will make this point of emphasis. We are saying the molar enthalpy will be for either the base or the acid, since both of them are responsible for the enthalpy change. 1 mole reacting with 1 mole here to give you a solution of sodium hydroxide plus energy. So the number of moles of sodium hydroxide, as can be recalled, for any solution, N is equal to C times V, using that solution triangle there. That's C and that's V, so we end up with that number of moles of sodium hydroxide. So watch this now. Calculating the enthalpy of neutralization with sodium hydroxide would be equal to delta H divided by N, and look, that was your delta H, that's the number of moles there, and this is the value that we get there for sodium hydroxide. Let's do it separately now for hydrochloric acid. The number of moles of hydrochloric acid is equal to C times V using this solution triangle here, and it works out to be the same as that for sodium hydroxide. And again, to find the molar enthalpy of neutralization for HCl, we use this relationship here, delta H divided by N, and it works out to be this. Look at this value here for HCl. I look at it for, anyways, they're both the same. If you're dealing with a monoprotic acid and a monoprotic base, and you're using equimolar quantities of both, then the molar enthalpy of neutralization can be used for either of them. So it wasn't really necessary for you to find this separately. But as a point of emphasis, I just did it separately for sodium hydroxide and also for HCl. Okay? So, quick review of that. If you want to calculate the molar enthalpy of neutralization for an acid and a base, you must have equimolar quantities of the acid and the base such that neutralization is complete. If not, then you'll have to find the limiting reagent and use the limiting reagent to find the molar enthalpy of neutralization. So to make matters easy, we started with this problem here that had equimolar quantities of hydrochloric acid and sodium hydroxide at the same initial temperature. So when you mix these together, the final volume that is produced will be equal to the volume of the base added to the volume of the acid. In this case, it worked out to be 100 milliliters, but there was a rise in temperature. So to find the delta T, we subtract the initial temperature from the final temperature. So carrying out all this operation here gives your Q or delta to be that, but this is only for a fraction of a mole of either the acid or base. Next job was to find the number of moles of either the base or acid, and that is what it was for sodium hydroxide. And then using this formula here, we calculated the molar enthalpy of neutralization for sodium hydroxide, and carrying out the same operation here, we got the same value here for the molar enthalpy of neutralization for hydrochloric acid. There is another problem here that's a little bit more challenging. We're having 25 milliliters of 1.0 mole per liter sulfuric acid at 20 degrees Celsius, and we mix that with 50 milliliters of 1.0 mole per liter sodium hydroxide, also at 20 degrees Celsius, and the final temperature attained was this. There is a number of differences in this problem. We're using half the volume of sulfuric acid compared with that of sodium hydroxide. But look, the concentrations are the same. Why do you think I deliberately use 25 milliliters? Because this is a diprotic acid here. So to get equimolar quantities of H and OH ions, I had to use only half of the volume of this acid here. Alright. Next difference is that we're adding 25 milliliters to 50 milliliters, so we'll only end up with 75 milliliters of solution. We can get this delta T by subtracting either of these from that, and now we can go ahead and find the heat gain by that volume of solution there. Q will be equal to M times C times delta T, and that's M because 75 milliliters, it will be 75 grams. This is a specific capacity for water, and this is your delta T. And it worked out to be that delta H or Q is equal to that number of joules. So now we go about and find the number of moles of the base and the acid. So the number of moles of sodium hydroxide used, since the solution, we use a solution triangle here, that N is equal to C times V, and we ended up with that number of moles of sodium hydroxide. And again, finding its molar enthalpy of neutralization, we utilize this relationship here, delta H divided by number of moles, and carrying out that mathematical operation, we end up with this value here. In the previous problem, that was the molar enthalpy of neutralization for sodium hydroxide. In this other problem here, it's the same thing. So if you're neutralizing sodium hydroxide with any other acid, the answer should be the same as long as they're strong acids. Now we can go about and find what is the molar enthalpy of neutralization for sulfuric acid. Again, now we have to find the number of moles of sulfuric acid in that volume there, and we use N is equal to C times V. C was 1 mole per liter, and that was V. C, 1 mole per liter, and that was V here. Should be here. That should be here. This 0 shouldn't be here. So the new number of moles should really be 0.025. So we did end up actually with the correct answer here. So note how the molar enthalpy of neutralization for sulfuric acid is twice that for the molar enthalpy of neutralization for sodium hydroxide, because look, you're using that number of moles of sodium hydroxide, but you're using only half that number of mole of sulfuric acid, such that when you divide, you ended up with twice the value, because you're having 2 moles of hydrogen in 1 mole of sulfuric acid. Alright? Since H2SO4 produces 2 moles of hydrogen per mole of acid when it ionizes, as such, it will produce twice the amount of energy as HCl, which ionizes to produce only 1 mole of hydrogen per mole of acid. How will the molar enthalpy of neutralization for calcium hydroxide compare with that of sodium hydroxide based on the problem that you have just done? What do you think? When you're neutralizing this, you're only neutralizing 1 mole of OH ions, and of course that will react with only 1 mole of H plus ions from some acid, right? So you get a certain value. Now look what happens. You're having 2 moles of OH ions. So to neutralize 2 moles of OH ions, you would have needed 2 moles of hydrogen ions. And of course, the enthalpy of neutralization will be twice that of sodium hydroxide. There's some questions here for you to do if you want to see those. You can pause the video and watch these and try working them.